Hi, my name is Reed Bailey, and this is a short presentation on problem formulation, the second step in the methodology presented by Gibson, Shearer, and Gibson in how to do systems analysis. There's another video on problem identification, the first step, that you really should watch before you watch this video. Now on this slide I want to introduce some terms we'll use in this presentation and map them back to terms in the Gibson, Shearer, and Gibson book. Discovery as a phase maps into steps 1 and 2 in Gibson, Shearer, and Gibson, which are goal development and establishing criteria. Creation looks at the divergent task of creating lots of alternatives, and that maps into step 3, convergence into step 4, which is ranking alternatives, and proposal into step 6, which is taking action. Now these phases can be explained in more detail into some steps: problem identification, problem formulation, alternative generation, evaluation, prioritization, and recommendations or action. And we'll see each of these has a group of steps that are associated within each of these areas. This presentation focuses most directly on problem formulation, systems, objectives, and metrics, and other ways of formulating the problem in terms of functions and requirements. Now, the fifth steps in Gibson, Shearer, and Gibson is iteration, and this entire process should be taken in a way that is willing to embrace the uncertainty and the unknown, to move forward, commit, explore the problem, explore solutions as a way of learning about the problem and the possible solutions. This is referred to as embracing error, and would lead to a design and an understanding of the problem that evolves over time. So iteration is a big part of this process. So let's get into it. Within the discovery phase, problem formulation. Once you understand what you think the problem is, how do we actually define that problem? So the primary focus in this presentation and on problem formulation is developing objectives and metrics. These objectives and metrics will help us in evaluating alternatives, and really the process of developing them is a critical part of helping the client better understand their own problem. A secondary focus in this phase is functional and design requirements, where functions more focus on what the system must do, requirements or constraints and limits on what the system must do, whereas objectives and metrics provide a direction of improvement. Functions and design requirements really just describe what the system must do, not what it must do to do things well. Doing things well would be more the objectives and the metrics. We'll discuss these in more depth in this short presentation today. Terms we use in this presentation: objectives, metrics, functions, requirements. The reality is, outside of this presentation, different people will use different terms to mean these same things, and sometimes they'll use these terms to mean different things than what we mean here. That's a reality. We're going to commit to using these terms in a certain way, but you should know as you go in the working world that you might find these concepts represented by slightly different words. In this presentation, we'll use the words objectives and goals equivalently, and metrics or indices of performance would also be equivalent. So we're going to jump right in and give you a couple of examples of the differences between objectives, metrics, design requirements, and functions. And one of these comes from an example project we worked on in laying out wine in a warehouse. In this case, one of the functions could be storing wine among many other functions. One of the objectives could be increase the amount of wine storage. We see there's direction to what that function. It's better if it stores more wine. A metric could be then the number of bottles stored. And then there could be a requirement, like a minimum level of bottles that need to be stored, 500,000 bottles or more. So collectively what we know is that it's got to store wine. We want to store as much as we can with a $500,000 bottle minimum. And the metric we'll use to measure this is number of bottles stored. Another project we can talk about is one we worked on concerning a vehicle miles traveled taxing or fund program for departments of transportation, where the idea is that revenue is collected not by a gasoline tax, but by how many miles you travel. So one of the functions is to collect money. One of the objectives is to collect money efficiently. It has direction to how money is collected. Metrics for this could be the cost required to implement a fee collection system, or the cost required to operate or run the fee collection system. And then a requirement could be that it shall not cost more than a certain amount per year to operate the fee collection system. Again, each of these types of terms, functions, objectives, metrics, requirements, describe something a little different in formulating the problem. One of the things you might have noticed is that objectives and functions are kind of similar, and they have some similar characteristics to them. One is that they're always a verb and an object. It could be collect money for a function, or reduce the time to collect money for an objective, giving it that direction. So reduce time to collect money, not just collect money, to be an objective. Functions could be, or would be, just collect money. These are objectives and functions of the system you're studying, not of the team. So it shouldn't say something like, to determine a way to collect money. That's your objective as a team. It's useful to know, but it's not useful in deriving metrics of performance that you can then use to evaluate alternatives. Your objectives and functions should be solution independent. It shouldn't be something that, in describing the objective or the function, limits your choices or alternatives artificially. This is a slightly different example I'm using here. For this one, to reduce the time to label a bottle after order is placed could be a better objective than to reduce time the print shop needs to produce labels. Because this second one assumes that a print shop is producing labels, as opposed to solutions might include that you produce your own labels, and really what you care about is just that the time required to label the bottle after an order is placed is minimized, and a print shop may or may not be part of the solution. And then you can structure objectives and functions as a hierarchical tree, where you start at the top and you break it down, and we'll show you an example of these. As you break it down, it gets into lower and lower sub-objectives, that if you were to do all the sub-objectives, you would be meeting the higher level objective, or if you were to do all the sub-functions, you'd be meeting the higher level function in such a tree representation. Now, metrics and indices of performance. These are going to be related to objectives and sub-objectives. Here's an example of a hierarchical tree of objectives. And the metrics essentially should be connected to each sub-objective, and they're how you're actually going to measure the objectives. So whereas objectives don't need to be measurable, metrics do. Whereas functions don't need to be measurable, design requirements do. And you can see this leap noted on this slide. This is indicating that there's not always a direct measurement for each sub-objective, and the idea is to get this leap to be as small as possible so that you're as directly measuring the sub-objectives as possible. So characteristics of good metrics, and also really for good requirements, they're measurable. A lot of times this means quantifiable, but not always. Something you can measure. It's objective. Different observers would agree on the measurement. It's meaningful. This essentially means that leap on that prior slide is as small as possible. It actually measures the objective it's supposed to measure. Doesn't specify a solution. Just like with objectives and functions, you want these to be solution independent. Understandable. You don't want to make something so complicated no one can understand it. And then for requirements, not for metrics, for requirements it'll actually set a boundary. So shall cost less than a certain amount. Require less than so many people to move this device that you're designing. Or as we saw earlier, shall hold at least 500,000 bottles of wine. So we're going to go into the winery warehouse layout example in more depth and show you how all of these four can work together. Now for any one project, you don't necessarily need to develop all four: objectives, metrics, functions, and requirements. But certainly you're going to be looking at objectives and metrics no matter what project you're working on. That's why they're the primary focus of this presentation. So here are some examples of objectives for the winery warehouse project. We want to effectively manage the storage of wine. That's a direction in the sense that we don't just want to manage it, we want to do it effectively. We want to organize the storage room, and we could say effectively, and track products within the facility effectively, which would again be giving some direction. Now as we go to the next slide, you're going to see this broken down, and you're definitely going to see the direction more clearly on some of the objectives for organizing the storage room. This sub-objective of organizing the storage room is split into 4 different sub-objectives. Maximize the total storage capacity, minimize the distance to different sectors of wine, and a sector in this project meant one type of wine goes in each sector, maximize the storage flexibility, and minimize inventory levels. Now it worked out that this project focused mainly on the first 3 objectives in this list, and so we can see metrics linked into these first 3 objectives. How are we going to measure total storage capacity? Well, the total capacity of wine, and the wine is stored at 500 bottles in a bin. Minimize the distance to the sectors. Well, we're going to look at the distance from the labeling line and the distance to the storage area. And thirdly, for maximizing storage flexibility, we'll look at the number of sectors in the layout, that is the alternatives, and also the number of different sector capacities that are available. These 5 measures that you see in this reddish color are the metrics that will actually be used to see how far we're progressing towards meeting these objectives. Now we can also look at the functional requirements of a warehouse, handle materials for, and provide information on wine varietals. Under the handling materials, it's wine, dry goods like bottles and corks, and unlabeled bottles. The dry goods also refers to the labels. And under that, what are the functions that has to happen? We have to input or accept materials, store materials, allow access to those materials, allow the materials to be moved around, and eventually release the materials so it can exit the system. Secondly, about the wine tracking the wine within the facility, provide managers with information of all the wine varietals, provide location information, and provide quantity of information for each wine varietal. Would be the functions. And you'll notice on these, it's just what the system has to do. It's not what it means to do it better. That's an objective if it was about what it means to do these things better. And then design requirements, we have a few slides of. You can see there's storage related things. We've seen the first one already, but shall be able to bottle and store an entire batch in one day is one of the storage related requirements also. Tracking related is that a manager should be able to figure out the quantity and location of a certain type of wine in no more than 2 minutes. That's related to the amount of time it would take to get back to someone on the sales team who needs to know how much is available. And access related, drivers shall be able to determine where to put wines in less than a minute. Drivers of forklifts, drivers shall be able to find wines in less than a minute. The minimum distance between stacks of bins shall be 10 centimeters. That third requirement is based on how tight a forklift driver can sit 2 bins down by each other without bumping into them. So 10 centimeters on each side is the minimum distance between the stacks of these 500 bottle bins of wine. So this is just showing you how we use this. This is not part of problem formulation, but ultimately we had the current layout, 2 alternative layouts, and you can see these 5 metrics that we saw earlier. Each of the 3 layouts is measured on these 5 metrics, and ultimately a recommendation is made on how well the different alternatives perform on the metrics. In this case, alternative B was a clear, superior alternative, but a lot of times you'll have conflicting alternatives where in order one will do better on certain metrics and the other will do better on other metrics. And then making a clear recommendation sometimes can be harder. That's further down in the process though. This is just to give you insight as to how these are used. So a summary here. At the high level we have objectives and functions. Objectives are derived from what it takes to move from the as is to the to be. Currently we store this amount of wine in the facility, and now we want to store a different amount or maybe more wine in the facility or store it more efficiently. They're directional. As an example, increase total wine storage capacity. Another high-level type of problem formulation is functions. This is just what the system does. These are static, they're not directional. This could just be store-wide. At the measurable level, not at the higher level we were a minute ago, there are indices of performance or metrics, and also such as, and also requirements. A metric could be something that's going to link in and measure how one objective is met, like, well, okay, if we want to increase the total storage capacity, well, number of bottles of wine is a good measure of that. Requirements are going to put limits or constraints, boundaries on what the system has to do in order to be just at a minimum level of requirements being met. Shall store at least 500,000 bottles. So you can think of the requirements as sort of just establishing the boundary in which all solutions that are viable must work, and then metrics say, once you're within that boundary, which solutions are better? What directions can you move within that boundary to look for better solutions? So a brief sort of visit to another perspective I'd like to give you. Think about, in order to get this perspective, this diagram is supposed to represent two different types of projects. You could have a project where you were closer to point A, where it's more about figuring out what to do, more planning and strategy, or one where you're closer to point B, whereas it's once you know what to do, how do you actually implement or realize that solution? And if we look here, the high-level, top-level type requirements for point A, objectives are more relevant. If you're closer to B, functions are more relevant. The measurable level definitions of the problem that are important. IPs are more important when you're more towards point A, where it's planning and strategy. And requirements can be more important when you're closer to B, which is more like design. You're realizing a system. Now you saw in our last example, we had all four of these things for one example. That's not always the case, but that means it's probably somewhere in the middle of this stage. And you can also think of at the bottom here, the design space, frequently alternatives might be used for different strategies, and then the word conceptual designs could be used for different designs if you're in the realization stage. So to wrap up, to summarize, we had talked about in problem identification this idea of generalizing the problem, the as-is or descriptive scenario, the to-be or normative scenario, and all of these things kind of combine to lead to your figuring out what the system's objectives are and how do you measure those with metrics. The objectives and metrics are derived from the as-is and what it takes to move from that to the to-be. And you have to make sure you're working on the right problem, and generalizing the problem will help make sure that the problem you're dealing with is indeed a root problem. These objectives and metrics help the client understand their own problem, and they're used later, as we saw in the wine warehouse example, to compare the different alternatives. And we also discussed functions and design requirements. These are analogous in some ways to objectives and metrics, but instead of focusing on what direction we need to improve a system, they just focus on the basic, what does the system need to do? Well, that wraps up the presentation on problem formulation from the discovery phase. And you've already seen the problem identification video at this point. These map to the Gibson-Shear and Gibson stage 1 and stage 2. That'll complete our set of videos for this discovery phase of the systems approach.